Safety considerations in a refrigeration plant extend beyond those directly related to the mechanical components. Refrigeration professionals must be knowledgeable about other hazards and safety considerations that may exist. Fire extinguishers are classified according to the type of fire they are designed to combat. Selecting the correct extinguisher is crucial for both safety and effectiveness. Class A refers to fires involving ordinary combustible materials, such as wood, paper, cloth, rubber, and certain plastics. The extinguishing agent for Class A fire is typically water, foam, or dry chemical. Class A extinguishers are marked with an A inside a green triangle. Class B fires involve flammable liquids and gases such as gasoline, oil, solvents, and propane. Foam, carbon dioxide, and dry chemical are common extinguishing agents for Class B fires. Class B fire extinguishers are marked with a B inside a red square. Electrical fires are Class C. Carbon dioxide and dry chemical are both effective at extinguishing Class C fires. Class C extinguishers can be identified by their blue circle with a C inside. Because dry chemical extinguishers are effective in stopping Class A, B, and C fires, they are commonly found in many workplaces and are identified by an ABC designation on the unit. Fires involving combustible metals are categorized as Class D. These fires involve reactive metals like magnesium, sodium, potassium, titanium, or lithium. Special dry powders designed to smother metal fires without reacting with them are used to extinguish Class D fires. Class D fire extinguishers are marked with a yellow star with a D inside. Class K designates fires involving commercial cooking appliances, animal fats, and vegetable oils. The extinguishing agents for Class K fires are wet chemical agents that cool and form a foam blanket over the oil. Class K extinguishers have a black hexagon with a K inside. Working around refrigeration equipment often involves exposure to high-voltage electrical equipment, from motor starters and control panels to variable frequency drives. One of the most serious electrical hazards in these environments is arc flash. An arc flash is a sudden release of electrical energy through the air when a high-voltage current travels between conductors or between a conductor and ground. The temperature in an arc flash can reach 35,000 degrees Fahrenheit, hotter than the surface of the sun. This intense heat combined with the force of a blast can cause severe burns, hearing damage, vision injury, shrapnel wounds, and even death. Arc flash is a risk for refrigeration professionals because many industrial systems operate at 480 volts or higher. Furthermore, frequent electrical troubleshooting and maintenance often increases exposure to live electrical parts, and limited access space in machinery and electrical rooms can make it harder to maintain safe working distances. The danger of electric shock to a human depends on voltage, current, exposure time, and the current's path through the body. While even relatively low voltages can be harmful, the general safety consensus is that 50 volts AC or higher is considered potentially lethal under the right conditions, especially if the skin is wet or the contact area is large. It's not just the voltage, current, or amperage that is the true killer. As little as 30 to 50 milliamps passing through the heart can cause ventricular fibrillation, a fatal heart rhythm. It is important that proper precautions be taken to prevent arc flash and electrical injuries. Always de-energize equipment before opening electrical enclosures or performing service. Use clothing, gloves, face shields, and hearing protection rated for the equipment's calculated arc flash energy level. Use a properly rated meter to confirm the circuit is de-energized before starting work. Respect the limited and restricted approach boundaries defined in NFPA 70E. Only qualified personnel with arc flash safety training should perform electrical work. Lockout-tagout, which is also referred to as LOTO, is a critical safety procedure that protects personnel from accidental equipment startup or the unexpected release of hazardous energy during service or maintenance. The main goal of LOTO is to ensure that all energy sources, including electrical, mechanical, hydraulic, pneumatic, and stored refrigerant pressure, are completely isolated before any work begins. This prevents injury from moving parts, electrical shock, refrigerant release, or sudden system activation. The key steps in a Lotto program are: trace all power and pressure sources connected to the equipment you will work on. Use normal controls to stop the operation. Open disconnects, close valves, and release stored energy. Secure isolation points with a personal lock and attach a tag identifying the technician, date, and reason for lockout. Test circuits and check gauges to ensure no energy remains before starting work. Only after verification should maintenance or repairs begin. Once work is complete, remove your lock and tag and restore the system following proper startup procedures. Refrigeration technicians often work in environments with elevated platforms, roof units, and mezzanine level equipment. Fall protection is critical to prevent serious injury or death from falls. OSHA generally requires fall protection when working 4 feet or more above a lower level in general industry and 6 feet or more in construction. There are many methods for protecting against falls. The best approach is to eliminate the fall hazard. Installing guardrails around elevated work areas is an example of passive fall restraint. When passive fall restraint is employed, a personal fall arrest system is not required. Active fall restraint involves a person wearing a full body harness that is connected by a lanyard to an anchor point that prevents the worker from reaching the fall hazard. If restraint is not an option, a personal fall arrest system, or PFAS, consisting of a full body harness, lanyard, and secure anchor point rated for 5,000 pounds per person, can be used to arrest a fall. Restricting access to areas where fall hazards exist is the final category of fall protection. Technicians frequently use ladders to access overhead valves, control panels, and rooftop units. Proper ladder safety helps prevent falls and injuries. Always choose the correct ladder type and height for the task. Ensure it is rated for the expected body weight plus any tools that will be used. Before each use, check for cracks, bent rungs, loose hardware, or slippery surfaces. When setting up a ladder, ensure to heed the following. For extension ladders, use the 4-to-1 rule. For every 4 feet of ladder height, place the base 1 foot away from the wall. Always secure the ladder to prevent movement. Ensure the ladder is on a stable, level surface. When using a ladder, maintain 3 points of contact, 2 hands and 1 foot, or 2 feet, 1 hand. Never overreach. Keep your belt buckle between the rails. Face the ladder when climbing up or down. A confined space is any area that is large enough to enter, is not designed for continuous occupancy, has limited openings for entry or exit. Some confined spaces may be classified as permit required if any of the following are true. The space has the potential for containing a hazardous atmosphere, such as a toxic environment caused by ammonia, oxygen deficiency, or flammable atmospheres. Contains a material that has the potential to engulf an entrant. Has an internal configuration such that an entrant could be trapped or asphyxiated by inwardly converging walls or by a floor which slopes downward and tapers to a smaller cross-section, or contains any other recognized serious safety or health hazard.
So a confined space is any space that's large enough to enter, not intended for normal human occupancy, and has a limited entry and egress. All right, that's the definition. It meets all 3 of those. So at an ammonia refrigeration facility, there are some spaces that are common confined spaces that you should be aware of. One is the diffusion tank. If the system is equipped with a diffusion tank. Now, that's not really much of an issue because no one should be tempted to enter the diffusion tank for any reason. However, it should be labeled as a confined space. The second, though, may be the condenser. Okay, evaporative condensers have access in order to get to the sump to inspect and clean it. And oftentimes, the access to those is limited. So limited entry egress is one of the defining features of confined space. So often the condenser will be a confined space when entering into the sump. And then third, this is a little bit unique to where we're located here in the San Joaquin Valley of California. But in cold storage rooms that use the bunker style arrangement, that space behind the bunker wall, which could be above or below the evaporators, could be considered a confined space. Again, it's going to be dependent on the configuration and what sort of access is available, but you want to be aware that there's requirements to enter these spaces that have the limited entry and egress.
Confined space incidents are often fatal because hazards can develop quickly and rescue is challenging. As a refrigeration technician, never enter a confined space without proper testing procedures and authorization, even if the task seems quick. A line break in refrigeration work refers to the intentional opening or disconnection of piping, valves, or components that contain or may have contained pressurized refrigerant, oil, or other hazardous substances. This task carries significant risks and must be approached with extreme caution. The line break procedure will describe the site-specific steps required to initiate a line break. Some best practices for line breaks include: identify and understand all contents, pressures, and hazards. Communicate the plan to all affected personnel. Lock out, tag out all energy sources, including electrical, mechanical, and pressure. Verify zero pressure using appropriate gauges before loosening any connection. Vent refrigerant to a recovery system, bucket of water, or flare. Never vent halocarbons directly to the atmosphere. Wear chemical-resistant gloves, a face shield, safety goggles, and insulated clothing for cold exposure. Establish a safe perimeter and post warning signs. Keep non-essential personnel clear of the area. Ice buildup in a refrigeration plant is more than just an inconvenience. It can pose serious safety risks, damage equipment, and disrupt operations if not addressed promptly. Ice formation is dangerous for a variety of reasons. Ice on floors, ladders, and walkways create immediate risks for slips, trips, and falls, potentially leading to serious injuries. Ice expansion can crack pipes, valves, and fittings, or place stress on heat exchangers and insulation. Ice on evaporator coils, air intakes, or vents can restrict airflow and reduce system efficiency. Accumulated ice can add significant weight to structural components, leading to deformation or collapse. In a refrigeration plant, ice is both a symptom and a hazard. Treat it as a warning sign. Address the root cause as well as the immediate hazard to maintain both safety and system reliability. Working in and around refrigeration equipment exposes technicians to extremely low temperatures from both the environment and the refrigerants themselves. This creates a risk of frostbite, a cold-related injury that can cause permanent tissue damage. Frostbite can occur through direct contact with cold surfaces or prolonged exposure to cold environments without the proper clothing. Frostbite is preventable by wearing proper PPE, avoiding bare skin contact with cold equipment, controlling exposure time, and ensuring that clothing is dry. Horseplay, any form of joking, roughhousing, or unsafe behavior, has no place in a refrigeration plant. In these environments, even seemingly harmless pranks or distractions can quickly escalate into serious injuries, equipment damage, or life-threatening emergencies. Always maintain situational awareness and a professional attitude at all times. Treat all plant areas as potential hazard zones. No running, pushing, or unnecessary contact with others. Jokes, pranks, or loud distractions can cause misunderstandings during critical operations or emergency response. If you see unsafe behavior, stop it immediately and reinforce a culture of safety. A hazard communication or HAZCOM program is a key safety requirement in refrigeration plants. Its purpose is to ensure that all employees understand the chemical and physical hazards they may encounter and know how to protect themselves when working around them. This program is not just an OSHA requirement, it's a core element of keeping people safe and ensuring regulatory compliance. Beyond the dangers of the refrigerant itself, refrigeration plants contain a variety of hazardous substances and equipment that can cause injury, illness, or property damage if mishandled. A HAZCOM program ensures chemical hazards are identified and labeled. A safety data sheet, or SDS, is readily available for each hazardous material. Employees are trained on the risks, safe handling, and emergency response procedures. Some common hazards in refrigeration plants include Chemicals used for condenser cleaning, water treatment, or scale prevention may be corrosive, toxic, or reactive. Without proper labeling and handling procedures, workers risk skin burns, respiratory irritation, or chemical exposure. Cylinders may contain refrigerants, nitrogen, or other gases under high pressure. Improper storage or handling can result in explosions, high pressure leaks, or toxic atmospheres. Boilers may contain hazardous treatment chemicals and operate under high pressure and temperature. A lack of awareness can lead to scald injuries, chemical burns, or equipment rupture. Lead acid or lithium-ion batteries are corrosive and may release explosive gas during charging. Mishandling or inadequate ventilation can cause chemical burns, fires, or explosions. Refrigeration technicians work in environments with pressurized gases, hazardous refrigerants, electrical hazards, rotating machinery, and extreme temperatures. Proper PPE helps protect against these risks and is often mandated by OSHA, IIAR, and company safety policies. Hard hats are required when working in areas where there is a risk of falling objects, especially in machinery rooms near cranes or during construction maintenance work. Safety glasses are used for general protection against debris, dust, and light chemical splashes. Chemical splash goggles are required when handling refrigerants, condenser chemicals, or other hazardous liquids. Face shields are used in combination with goggles during line breaks, charging operations, or where there's a risk of liquid refrigerant spray or arc flash. Chemical-resistant gloves must be worn for handling refrigerants, condenser treatment chemicals, and battery acid. Insulated gloves are needed for protection from extreme cold. Electrical-rated gloves are required when performing energized electrical work. Steel toe or slip-resistant boots may be required to protect against dropped tools, heavy equipment, and slips on icy or wet surfaces. Coveralls made from durable, flame-resistant fabrics are recommended in areas with welding, cutting, or arc flash risks. A chemical-resistant apron is used for oil draining or when handling other hazardous chemicals. Cold weather clothing, such as insulated jackets, bib overalls, and thermal layers, are for extended work in cold storage areas. Air purifying respirators with appropriate cartridges for ammonia, halocarbons, or other hazardous vapor are used for exposure to known concentrations of hazardous gases. A self-contained breathing apparatus, or SCBA, is required for emergency entry into areas with high toxic concentrations or oxygen deficiency. Earplugs or earmuffs are required for high-noise areas, such as machinery rooms. Arc-rated clothing is necessary for electrical work with potential arc flash hazards, including arc-rated face shields and balaclavas. Fall protection equipment, including harnesses, lanyards, and anchors, are required when working at heights on platforms, rooftops, or ladder access equipment. PPE selection must be task-specific, properly fitted, regularly inspected, and used in conjunction with safe work practices. For refrigeration technicians, PPE is the last line of defense, not a substitute for hazard elimination or engineering controls. Hot work refers to any task that produces flames, sparks, or heat sufficient to ignite combustible materials. In refrigeration plants, this includes welding, cutting, grinding, brazing, or soldering. Because these facilities contain flammable materials, refrigerants, oil residues, and insulation, hot work poses a significant fire and explosion hazard if not properly controlled. Safe work practices must be adhered to when performing hot work. Always follow the facility's hot work permit procedure. Ensure hazards are identified and controlled before work begins. Remove or shield combustible materials within at least 35 feet. Ensure ventilation is adequate to disperse fumes and gases. Assign a trained fire watch to monitor the area during and after hot work. Maintain fire extinguishers nearby and ensure a fire watch remains in place for at least 30 minutes after completion. Wear flame-resistant clothing, welding shields or goggles, gloves, and hearing protection as required. Verify that refrigeration equipment is de-energized, depressurized, and properly isolated before beginning work. Never perform hot work on lines or vessels that may contain refrigerant or oil. In refrigeration systems, trapped liquid occurs when refrigerant becomes isolated in a section of piping or equipment between two closed valves. Because liquid is nearly incompressible, even a small temperature increase can cause a rapid and dangerous pressure rise in the trapped section. Trapped liquid is hazardous because as the liquid warms and expands, pressures can exceed the design limits of the pipe or vessel, leading to ruptures and refrigerant release. Burst piping, valve failures, or ruptured components are examples of equipment failures that can result from trapped liquid over pressure. The refrigerant release is dangerous because the discharge will be high pressure and may be toxic, flammable, and extremely cold. Refrigeration operators must be conscious of the safe practices for trapped liquid. Never close liquid valves in a way that isolates the refrigerant without a relief path. Confirm pressure is fully relieved before loosening fittings or opening a line. Wear gloves, face shield, and protective clothing when working around liquid refrigerant piping. Trapped liquid is a hidden but serious hazard in refrigeration systems. Even small volumes of refrigerant can create dangerously high pressures if isolated. Always assume pressure may exist, follow the proper line break procedures, and handle valves with caution to prevent catastrophic failures. In refrigeration plants, emergencies such as ammonia or refrigerant leaks, fires, or equipment failures can create conditions that require immediate evacuation. Being prepared and knowing the correct procedure can save lives. Be familiar with how the plant signals an evacuation. Common examples are sirens, strobes, and PA announcements. Always know at least 2 safe ways out of your work area. Leave tools, parts, or ongoing tasks behind, focusing on reaching safety quickly. Alert coworkers, especially if they are in confined or high-noise areas. Once outside, go directly to your designated muster point for a head count. Never re-enter until cleared by emergency responders. Windsocks, typically installed in highly visible areas at a refrigeration plant, indicate wind direction and strength. In the event of a refrigerant release, vapors will travel with the wind. Employees must be trained to locate the windsock immediately to evacuate upwind or crosswind of the release. Always move perpendicular or against the wind direction to avoid exposure. Refrigeration systems contain many types of rotating machinery, including compressors, pumps, motors, and fans. These components are essential for system operation, but pose serious hazards if technicians are not properly trained. Some key safety practices for working around rotating machinery include: always isolate energy sources and verify equipment is fully stopped before performing service. Never bypass or remove machine guards while equipment is running. Guards are designed to prevent accidental contact with rotating parts. Safety glasses, hearing protection, and snug-fitting clothing are critical when working near rotating machinery. Stay clear of rotating shafts, couplings, belts, and fans when equipment is running. Verify guards are in place, fasteners are tight, and components show no signs of wear or damage before starting equipment. Wait until all motion has stopped before approaching machinery. Flywheels, fans, and motors may take time to wind down. Forklifts are one of the leading causes of workplace injuries in industrial settings. As a refrigeration technician, the best protection is constant awareness of forklift traffic, especially when entering or exiting rooms. Pause, look, and confirm that it's safe before stepping into a new area. Safety vests or bright clothing are helpful to make you more noticeable in dim or obstructed areas. Never walk directly behind or beside a moving forklift and maintain a safe distance when they are operating. Never assume a forklift driver sees you. Establish visual contact before crossing paths.
So I really think one of the most dangerous things that I do in my job is when I visit a ammonia refrigeration facility isn't the ammonia itself, but it could be the forklift traffic. So it's really important that you be aware of traffic when you're at a facility, especially when entering into a room or exiting a room. Always use a man door if one's available. And if you do have to walk through a roll-up door that has forklift traffic, make sure to heed all proper safety precautions. Make sure one isn't coming first, and don't just exit or enter straight through the middle of the door. Keep right toward the edge. Forklift drivers should be trained to honk the horn as they're going in and out, and lots of them do that. But if you check the walls, you'll probably see little dings, and you don't want to be caught up in that.
Refrigerants have the potential to create dangerous atmospheres, either toxic, corrosive, or oxygen displacing if a leak occurs. Respiratory protection awareness is critical to protect health and ensure technicians can safely respond or evacuate during emergencies. There are several different categories of respiratory protection that a refrigeration professional should be aware of. Air purifying respirators, or APRs, use cartridges or filters to remove contaminants from the air. They have limited use because they are only effective when oxygen levels are safe and contaminant concentrations are known and below IDLH. Supplied air respirators and self-contained breathing apparatuses, or SCBAs, provide clean air from a cylinder or remote source. These units are more expensive than APRs and require additional training and medical monitoring, but are required in atmospheres that are oxygen deficient above IDLH or unknown. Emergency escape breathing apparatuses, or EEBAs, provide compact, short-duration air supply, typically 5 to 15 minutes. EEBAs are designed for emergency egress only, not for performing repairs or extended work.
So each respirator type is limited in a different way. There is no perfect respirator. So let's start with an air purifying respirator. That's a cartridge style respirator. And the air purifying respirator is limited in two major ways. First, it is only capable of filtering out certain concentrations of chemicals. So if you exceed that concentration limit, the cartridge will be ineffective and you could still be exposed to hazardous chemicals. All right. And second is the air purifying respirator does not supply any oxygen. So it's a worthless device. It's worthless protection if you go into an oxygen deficient atmosphere. It won't do anything for you. So those are the two main limitations of an APR. Second, we go now to the supplied air style of respirators, the most common being the self-contained breathing apparatus, or SCBA. Now we've got a tank of clean air on our back. So now our limitation is that tank itself, because that only has a finite supply of air for us to breathe. So it's very important that that gauge be monitored and you don't exceed that, because again, you'll run out of oxygen. A second limitation for an SCBA would be just mobility, because you've got this thing on your back now. It makes it a little harder maybe to climb a ladder or get in through a small opening. Okay. Third type of respirator. A third type of respirator is the supplied air respirator. Like an SCBA, we are now connected to a tank supplying oxygen, but now that tank's far away, it's not on our back. So theoretically, it's like an infinite supply of air. Maybe not infinite, but it's a very large supply of air. Now our limitation is the length of the hose, right? Because we're connected to that by a hose, and we'll be limited on how far we can actually travel. But our mobility may be a little bit better because we're not wearing it on our back, and the total supply is greater than that of an SCBA. And then the fourth is the emergency escape breathing apparatus. Now, technically, this is not a respirator per se, but I do want to talk about it because we see them, especially at ammonia refrigeration plants. And the emergency escape breathing apparatus is essentially a bag that you put over your head and then open a valve to supply air into that. And that is for escape only. So it's very, very important that we say that clearly. The emergency escape breathing apparatus should never be used to go fix something, to go investigate something. It's used for escape only. Sometimes that's even called self-rescue, like you're rescuing yourself. You can throw that thing over your head, give yourself some oxygen, and get out of there.
Respirator fit testing is a required procedure that ensures a tight-fitting respirator, such as a half-face or full-face mask, properly seals to a worker's face. Without a correct fit, contaminated air can leak around the edges of the mask, reducing its effectiveness and placing the worker at risk. There are two types of fit testing. A qualitative fit test is a pass-fail test that relies on the wearer's ability to detect a test agent and is used for respirators that require a fit factor of 100 or less, such as half-face masks. The fit factor is a numerical value that represents how well a respirator seals against a wearer's face. It measures the ratio of the concentration of a test contaminant outside the respirator to the concentration inside the respirator when the mask is worn. A quantitative fit test uses specialized instruments to measure actual leakage into the respirator and provides a numeric fit factor which is required for respirators that need a higher level of protection, such as full-face masks.